Okay, so we are back with the second talk. We've been having, as I like to mention, talks from all around the world. We just had one from China. Now we have one from the deep north. So we have Cordian all the way from Norway. Please, Professor.
Thank you very much for the nice introduction. Indeed, I'm on the northernmost university in the world. So, and this is in the evening for me. It's morning for you guys. So, good morning, good evening, good night, whatever you are. I'm sorry that yesterday we had these technical issues, and I hope it now works. But I updated my Wi-Fi, so it should actually work. And without further ado, I would like to present some work that touches on algebraic combinatorics, symmetric functions, and is joint work with several people. And I just have to see. Yes. So, but before I start, let me just talk give you one beautiful first picture that you maybe want to remember for the rest of the talk and also maybe beyond. So, I mean, one of the fundamental philosophies of mine is that symmetry is a very nice thing in that sense that it helps you to describe something in a very simple manner. So if you look at this kaleidoscope that some of you maybe remember from your childhood, I mean, you all agree that, I mean, although this is a very complicated picture that we get in the kaleidoscope, so potentially here infinite also, I mean, all the information that we need is in this small inner fundamental domain that you maybe see. I don't know if you can see my cursor actually. Um, that you see in this in a fundamental domain. And so with a finite information in this inner domain, we can create here a periodic infinite image that is very complicated. And this actually this philosophy mirrors some of the works that I do, and in particular, it mirrors something that I want to present today. But we're not talking about pictures and about arts, but we talk about polynomials. And I want to start with a motivating example of the talk. So suppose I give you the following expression, namely, I give you what we call a trace polynomial, which is I gave you an expression that is written down in the products of traces of powers of matrices. So for example, 2 the trace of a squared times the trace of b to the 6 minus the trace of a to the 4 times b to the 4 plus and so on. So this can be homogeneous, but I mean, so this would be a homogeneous trace polynomial in three variables, a, b, and c. Okay. So a trace polynomial is I can view it as a function. I take 3 matrices, I give it to this expression, and I get a number, and I can ask myself, do I get a positive number or a negative number? And I say that the trace polynomial is non-negative if whenever I give him matrices, I get only non-negative numbers. And the crux here is that I want to be able to give matrices of all sizes. So I have a finite expression here, like in this example, and I want to know if Federico chooses arbitrary 3 matrices ABC of arbitrary sizes, will I always get a non-negative number? So the input is the sequence, and the question I want to ask is the number always non-negative? Okay. So far, so good. And in mathematics, you should do it unlikely as in jokes. You should spoil the story already from the beginning that you can follow much easier. So the first spoiler is I want to convince you that this problem is undecidable. And second spoiler, which is a little bit maybe also interesting, is that this problem actually is decidable if we replace the trace by what we call the normalized trace. I will come to this in the beginning. So, I mean, at first you would think maybe this is obvious. Why should this be decidable? I mean, I have all of these sizes and so on. I mean, it seems to be a hard problem. But if we relax this problem a little bit by talking about normalized traces, it suddenly becomes a very easy solvable problem. Okay. Is the motivation understood? Everybody fine? If you have any questions at any point, feel always free to jump in. I hope we have the time. So of course, this is nothing new to you. So there are symmetric polynomials, and I love symmetric polynomials, like I hope everybody in this conference does. Elementary symmetric polynomials and power sums polynomials are very important, and they are related. You all know all of that. They are related by the Newton identities. Why do I care about power sum polynomials? Well, I mean, this may also not be a big surprise to you. I mean, if we remember also from linear algebra that the trace of a power of a matrix is just the power, the sum of the powers of the eigenvalues, then actually I can reformulate this fancy looking problem with matrices into symmetric polynomials. So if I start by this 2 times trace a to the squared b to the 6, I mean actually I'm talking about these polynomials that I have here, um, um, transferred in power sum polynomials evaluated at eigenvalues. Okay, so the same question to ask if this trace polynomial is non-negative for all matrices of all sizes a, b, and c is the same as to ask, does this expression that I now write down here in power sum polynomials stay non-negative for all values x, y, and z, where x, y, and z are now potentially infinite sequences of numbers, growing sequences of numbers. Okay, so I mean, obviously these questions are the same. So this leads us to the tool, and actually, so I mean, more interesting than I mean, that this is an undecidable problem because maybe you never had this problem in your life before, so you don't care too much about it being undecidable, is the reason why it is undecidable, and this has something very nice to do with a map that I want to introduce now. And this is what we call the Vandermonde map. So the Vandermonde map is also a very simple map. It's just you take a point with positive or non-negative coordinates and you map it to the first d power sums. So this is a map from Rn, n bigger than d, to Rd. It maps down from Rn to Rd. And if you want, I mean, looks very special. You could also allow your power sum polynomials to have any non-negative exponents, even rational exponents. But I mean, for the rest of this talk, I will just fix this model. And now we take the standard simplex in Rn. So this is just the non-negative points where we normalize the sum to be 1. So this is a nice simplex, and we feed it into this map. So this map goes from Rn to Rd, and the image of this map is a d-dimensional set that we call the Vandermonde cell. So n because I start in n, and d because I go to d dimensions. So actually, I mean, n minus d because I mean I have this normalization hyperplane here. Okay, and I mean in the inverse image, I start at the point in the image. I look above on the fiber above this point. I get a variety upstairs, and this is what we also call Vandermonde variety. So Vandermonde VAP, Vandermonde cell, Vandermonde variety. So I think everybody has heard the name Vandermonde in their lives before, but let me just come with a small historical remark. Who was Alexander Theophil Vandermonde? So he was a mathematician, of course. But when we talk about Vandermonde, we mostly think about exactly this matrix and its determinant, the Vandermonde matrix and the Vandermonde determinant, which has this very nice property that it factors rightly into the hyperplanes that define the reflection hyperplanes of the group of the symmetric of the action of the symmetric group. So who was Alexander Theophil Vandermonde? He was a mathematician in the 18th century in Paris. He was very interested in solving univariate polynomials, of course. And I mean, according to some people, he never really studied this this matrix that now bears his name, or this determinant, which brings me to another important figure that you will see in the talk a little bit, Vladimir Igorovich Arnold, who has a very fascinating Arnold principle that applies in the same, which is if a notion bears a person's name, then this name is not the name of the discoverer. So this is in particular true for Arnold. And for those of you who don't want to follow the talk anymore, I challenge you now to think about if the Arnold principle applies to the Arnold principle. Very good. Okay, let's go back a little bit. So these Vandermonde maps have, of course, appeared in many different areas before. So they appear in the relation to inequalities of p-norms in a work by Ursel in the 50s. as I mentioned, Arnold, Giventhal, and Kostov, people in the Arnold school, looked at this map in relation to univariate polynomials, hyperbolic polynomials, the polynomials that have only real roots, because I mean that's just the pre-image of such a map. And in works with Shogata Basu, we actually were able to study these things in relation to the homology of symmetric semi-algebraic sets. And in a recent paper, people also studied this map using computational algebraic geometry. So this is a very well studied map. It's very beautiful, and the next 20 minutes I want to convince you that this is a very beautiful map. So the first result that I want to mention briefly goes back to Arnold, Giventhal, and Kostov, which is essentially that this map, the varieties, so the pre-image of this map has a very nice property. Namely, I mean, it's not a contractible variety, but when you intersect the variety with a fundamental domain of the symmetric group, so with a Weyl chamber, or it's contractible. So, or equivalently, its equivariant homology is trivial. So this actually means that this map up to the action of the symmetric group has very nice, very tame fibers. And so this is actually something that is very useful, in particular in this work with Chogata, that we use this for actually understanding the topology of symmetric semi-algebraic sets. Okay. So morally, these Vandermonde varieties, they are very tame fibers, and that actually allows us to understand the geometry of symmetric sets in general much more easy. Okay, so why do I care about the Vandermonde variety? Of course, that's also the Vandermonde cell. That's obvious. I mean, if I give you a symmetric polynomial in n variables, you all know that any symmetric polynomials in n variables can be written as a polynomial in the power sum, Newton sum polynomials. And in particular, if we fix the degree of our polynomials to be d, some arbitrary d, then I will only need to write it down with the first d power sums. So, and then obviously, if I have a solution upstairs, f of x that evaluates to f of fi of x equals 0, then this will give me a solution of g of y equals 0, and the solution will lie in this image. And only if I find a solution of g of y I equals 0 in this image, I can lift it back up to the pre-image. Okay, so there is this connection of I have a solution. I'm positive. I'm positive upstairs if and only if G is positive on this image of the map. Obviously, that's just a composition of maps, nothing deeper. Okay, and because the fibers are so nice, you can use this very nicely to analyze the sets that you get downstairs. But that's maybe not so interesting. So let me show you first a picture of a Vandermonde cell. So this is a picture of a Vandermonde cell. And I think it's the case when we go from R8, I think, to R2. So we fix P2 and P3. So we map on P2 and P3, and because P1 is equal to 1. So this is one example of a Vandermonde cell that I wanted to show you. And now I want you to imagine you take, I mean, for those of you who are sitting in front of your screen and have glasses like me, they take off your glasses. And for those of you who sit in the classroom, maybe you do the same. So just kidding. So what you see is, if you look at the lower part of this map, it looks, I mean, at first very like straight lines. Yes, they are curved. But if you weren't able to see this curvature, is there anybody who can have a guess what you would want to, what you can see here? Is there anybody who thinks this looks like something I've seen in my life before? Not important. So we will come to the solution. Yes?
Gordon, one quick question. So you said that you map P2 and P3, but what is the domain? I see 9 vertices, so you are mapping from like a simplex
R9, I'm
dimension
marking
8?
from R9 to R2, because I mean,
Okay.
P2 and P3, and P1 is fixed.
And the vertices are the vertices, the images of the vertices.
Exactly. I mean, I mean, you have a simplex upstairs. You map it to the vertices of this thing, but I mean, we call it vertices. I mean, because I mapped it like this. So, And I mean, what I wanted to say, it looks a little bit like a polytope if you forget that this green line is extremely curved and everybody can see that it's curved. These other lines look a little bit more straight, maybe, so you would actually be very likely to mistake it for a polytope. And the question is if everybody has an idea which polytope this might be, but we'll come to this in a split second. Yeah, but I mean, this is one example of a Vandermonde cell. Okay, so what is nice about this Vandermonde cell is that you can actually describe its boundary very nicely. I mean, as Federico already said, I mean, the vertices will come from vertices, but I mean, to understand the whole boundary, like which points are the points that are mapped to the boundary and whose image is enough to reiterate the boundary, there's a very nice result that actually was already proven by ourselves, but we gave a new proof for that. And that says as follows. So I mean, the boundary is obtained if I evaluated points in the simplex with at most d distinct coordinates. So I'm in Rn, n is bigger than d. I only evaluated d distinct coordinates, non-negative coordinates, because my simplex has non-negative, so I can order them. And 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 I mean either the first, I mean either they are zero, yeah, and then I have one of the coordinates is special, and then I have multiple times the second coordinate, and then I have a third coordinate which is again special, and then I have multiple and so on. Or I have no zero to start with, then I start with x1 several times, and then the second one again is special. So it's always coordinate is many times there, one time there, many times there, one time there, many times there. Okay, and in total we have at most d of them, including zero. Okay, so if I look at all of these, so these points, they live in Rn on specific d-dimensional planes, yeah, namely the ones where we set the coordinates to be equal, and only looking at these points, I get exactly all of the boundary. So as I said, this result is very, I mean, is easy to get, or very easy to get once you see something that is very nice about the Vandermonde map. And this goes back to Arnold and Kostov. So I mean, you fiber your image by actually these Vandermonde varieties. So you fix for a given set of parameters, you fix the power sums. This is a compact variety, and connected, and it's or empty. um, and I mean the trick that you do for that is you look at the Lagrange function and just at the derivatives. And now I mean the thing, and this pulls back to this Vandermonde, is if you look at power sum polynomials and you look at their Jacobian, you get exactly a Vandermonde matrix, right? And this is, and so the determinant of that really is this hyperplane arrangement that you have upstairs, which sort of explains exactly why you have at most d distinct coordinates, and then you have to do second order sufficient necessary conditions to actually see that you have also this multiplicity pattern in here. So this is a very easy proof actually that you could do with first year calculus students or second year calculus students. Okay, so now I want to come to this thing that I wanted to say. What is the thing that I wanted you to recognize here? So all of you know what a cyclic polytope is. If you don't know what a cyclic polytope is, well, here's the definition. It's just a convex polytope whose vertices are exactly on the d-dimensional moment curve. So I take points in the d-dimensional moment curve, I take the convex hull, the thing that I get is a convex polytope, and I call this a cyclic polytope. And the combinatorial structure, so the number of faces, is independent by the chosen points. That's also something that was shown already in the 60s by Gale, and it's characterized by this Gale's evenness condition that, I mean, pretty much I assume everybody in the room knows. So I mean, points on the moment curve form a phase if and only if they meet this evenness condition of Gale's. Very good. So now comes the thing that I said why it's good to keep off the glasses and maybe see the picture a little bit from a distance. The following definition: we say that a set has the combinatorial structure of a cyclic polytope if we can find a homomorphism from the boundary of a cyclic polytope to the boundary of the set, which becomes a diffeomorphism when we restrict it to the relative interior of the boundary. So, and then the vertices are exactly the vertices of a cyclic polytope. So, so just to say again this example here, yeah. So I mean these are the vertices, yeah, and I want to think these as the images of faces of a cyclic polytope, yeah. So they are, I mean, and this is now here you would, I mean, maybe you have realized a cyclic polytope with sort of uh, deformated faces because they are curved here. So this is the intuition that we want to have. Okay, and the first interesting result that we could show is actually that this set actually has the combinatorial structure of a cyclic polytope. So it's actually, you can always get a cyclic polytope, and this is essentially its boundary is glued by patches, sort of where each patch is a curved simplex. You don't have a simplex, but you have a curved simplex. Okay. So, as I said, I mean, one could also have looked at the elementary symmetric polynomials. I just do this for a split second here. So, I mean, then you get another image, but Newton's identities, of course, give us that these two sets are diffeomorphic to each other because I can express the Newton via the Newton identities, the elementary symmetric polynomials in the power sum polynomials. And so the interesting thing is there's a result that goes back to Bolabash in the 70s, but independently was found by Alexander Kovacs, Salma Kuhlmann, and myself, is that when you look at the convex hull of such a thing, then you can actually write the convex hull of this thing down as as a convex hull of these points. Okay. So it's also a cyclic polytope. So the convex hull is a cyclic polytope, and this convex hull is the convex hull of the elementary symmetric polynomial. So I mean, not only is this thing, I mean, obviously this thing is diffeomorphic to a convex polytope, so it's convex hull. If you look, the elementary symmetric polynomial also is an honest cyclic polytope. So now I want to come to the part when I say, okay, now we've looked for one fixed n, such a point, but we're interested in actually asking us, I want to include all length of parameters. So what happens if I go from n to n plus 1 variables? So this is not really well maybe visible, but you can see here I magically added one additional point, and these points are all on the two-dimensional moment curve. And so what we get, I mean, you see this green line is a little bit thickened. So actually these are two green lines. So I go from 8 to 9 or from 9 to 10. And what I do is I just add another point down here and I get a new upper patch. And so my previous set is included in the new set. So I get a bigger set, but actually I just get it by adding a new curved simplex to it. So the first thing is, I mean, when you want to decide if a function is non-negative with a set, you're pretty well off if the set is semi-algebraic. Semi-algebraic is a set that can be described by polynomial inequalities. So the first thing to show is that, I mean, if you look at now if you let n tend to infinity and we look at the union of all of these sets and we take the closure, obviously if my function is non-negative on this set, this closure, the union of the closure of the unions, then we have this property that it will be non-negative for all entries that I get to it. And this if this union were semi-algebraic, if I could write it down with honest function, with only polynomial functions, then you could use things like Tarski transfer principle to actually decide non-negativity easily. But I mean, the first thing to show is that these sets are actually non-semi-algebraic as soon as d is greater than 3. And the reason is very simple. I mean, you can see this here, or you can see this in the previous thing. We always added another vertex. Vertex are singular points, so I have a set that has infinitely many isolated singular points, and there's no way I can describe such a set with polynomial inequalities. So let me just now try to also tell you when there's something more that is the driving engine of the undecidability result, and for that we need to increase the number of variables, but maybe that's not so interesting. So this thing is undecidable, and the way to prove this is by going through another undecidable problem. So I mean, normally, I mean, not a computer scientist, but my naive way of proving undecidability is you have an undecidable problem that we know is undecidable. I have a problem. If I can show that could I solve my problem, I could solve your problem, then my problem also has to be undecidable, right? So, and this is exactly what we do here. And the problem that we are building it back to is essentially Hilbert's 10th problem, which is deciding if a polynomial has zeros on the integers in many variables. And that's, if you have many variables, is undecidable. It's easy for univariate polynomials, but it's undecidable for higher polynomials. And as I said, a slight adjustment, if we take normalized trace instead of traces, it actually becomes decidable. Okay, so this just to say, this goes back to work of Hatami Norin, who did this with linear graph homomorphism densities. So we essentially adapt their deduction here. Okay, let me just here just you see, I mean, you get all of these infinite points that you have to be non-negative on, and thus if you are not non-negative, I mean, so this brings it back to the integers. Okay, I mentioned that when you do it for the normalized traces, it actually becomes nice, and this is because if you do it for if you take power sums and you normalize, this has a natural connection to measures on the real line. So you actually come to measures with bounded complete mass, and the set that you look at is a so-called Hankel spectrahedron, where you actually can write down inequalities nicely. So it is semi-algebraic, and then the semi-algebraicity gives you the whole set. And this was independently studied by other authors before us for this normalized traces. So open questions, there's still a lot of open questions. I mean, for example, as I said, univariate polynomials are decidable over the integers. Here we have not been able to show that univariate trace polynomials are different in some sense. It would be very interested. We're also not sure if how to actually quantify that strict positivity should be easier to decide. And so now maybe you had fallen asleep, and now it's the moment to wake up again for a split second, because I want to thank you for the attention. But before you clap, let me just show you this picture. So this is the northernmost, this is how the place where the northernmost university in the world looks like. So for Canadians, this might be also not so spectacular, because if you live in northern Canada, you see the aurora borealis. But if you come to Tromsø, you can see it in the winter, you see the midnight sun in the summer. And I just wanted to mention that we are building up a research center for math here in northern Norway, and we are looking for people who are interested to run a thematic workshop in 2027. So if you're interested, feel free to reach out. Thank you so much.
Thank you, Professor. Wonderful talk. We have questions. We have time for some questions. Does anyone have any question or comment?
Yes.
Yes.
Sorry.
So I know what tradition this is in. I've seen a lot of people doing like AMGM for matrices instead of numbers and things like that. Do you suspect that any of those classical like inequalities are actually undecidable? Because I know some of them are open.
That would be I mean, so exactly, we don't know any. It would be nice to show something like this. We have not been able to show this, but I would hope, I mean, at the moment, this is just a theoretical result. But we have to rely on this deduction, but having really one would be really great.
I have a question myself. When you map the simplex, then you get this what you call Vandermonde cell.
Yes.
And this thing looks like the cyclic polytope.
Mm-hmm.
And you say that it's not really the walls are not really straight; they are curved.
Yes.
Are they curved like inside or outside? So is this thing a subset of the cyclic polytope, or it goes outside?
So it's curved inside. Let me
Inside. It's a concave. All these things
exactly,
like
exactly. So I mean, okay, okay. I just also mentioned. So I had another PhD student who, I mean, not with this particular thing, but he looked at other things that have the same sort of curvedness, and he called them starved polytopes because somehow sort of, they didn't get enough food, so they are very slim and
Nice.
yeah.
Okay. Any other questions?
So you were focusing on the trace, but in theory, you could ask about other coefficients of the characteristic polynomial of matrices. Does that, I mean, I guess, is that included in what you do just for
No,
abstract
it's not yet
reasons?
included. It's a good question. I mean, it's not included. I mean, I would guess the same sort of, deduction would maybe work, but explicitly we have not done this, no.
Thank you.
Okay.